All right, everyone. Chapter 27, Wave Optics. So we're going to go back to the wave properties of light and try to understand some of the things that cannot be explained with geometric optics. Ray diagrams are very useful for mirrors and lenses, but there are other things that we can look at, like interference or diffraction, that cannot be explained with geometric ray optics. That means the ray diagrams or ray model is not very useful for interference and diffraction. So that's why we're going to have to go back and look at the wave model of light to understand some of these properties. Because in physics 66, we went over some of the properties of waves when two waves can interfere with one another. And those properties, remember, were unique to waves. And we had to think of them as waves, two waves moving with some velocity. They overlap at some instance of space and time, and then they can interfere either constructively and destructively. So that's kind of what we're going to be looking in this chapter. So remember, constructive interference is when you have two waves. So let's say here's wave one moving to the right, and then here let's make it a different color maybe. All right, so here's wave two moving to the left. And when they overlap, then for example, here's the instant when they overlap. So let's say if this is wave two, and let's say this was wave one. So if they overlap what we call in phase, that means their crests and crests overlap and troughs overlap. So this is known as the constructive interference. That means, their crests and their troughs overlap at the same exact space and time. And one of the things we do here is, so let's say if this is amplitude plus 2, this is amplitude plus 2, then when they overlap, they generate a new wave, which is generally what we call superposition of those. And amplitude of this either, basically it's algebraic sum. That means either larger or smaller than individual waves. So in this case, the amplitude is going to be then plus 4, because plus 2 and plus 2, right, going to add up, and then you get basically plus 4 in terms of the amplitude. And constructive interference basically assumes that they are what we call in phase, meaning that they are moving such a way that every time you put them together, right, on top of each other, even if they are, let's say, coming from two different flow sources, moving two different distances, they will still be, on top of one another in terms of like crest and a crest, trough and a trough, and then you're always going to get increase in the intensity of the signal. So basically, all right. So you can also get a destructive interference. In the destructive interference, you kind of have the opposite. So let's say here's your wave one moving with some velocity here. And let's say here's your wave two moving with another velocity like this, right? But when they overlap, so let's say this was the wave two. So the wave one then will be such that when they overlap, wave one will be like this. Okay. Meaning the crest of the wave two will overlap with the trough of the first one, or the trough of the first one with the crest of the second one. And that, as you put them together, right, in terms of superposition, right, then that's going to create a new wave, which is again, in terms of its, amplitude will be superposition, right? It will be algebraic sum. And if there's, let's say this is plus 2, and then it overlaps with the trough, which is -2, right? So then they basically are going to cancel each other, and you get what we call destructive interference, where the amplitude of the resultant wave is less than that of either individual waves. That means what we get here is destructive and constructive interference, and this is very unique to waves. No other thing can actually interfere like this. Two things that have matter, right? When they try to go over one, through one another, they can't. They try to do that with two pencils, right? They can't go through one another. But to sound waves can, to light waves can, to water waves can, right? So those are very unique to waves. That's why all interference associated with light waves arises when the electromagnetic fields that constitute the individual waves combine. So we are assuming that this is true for any waves, and since light is an electromagnetic wave, this is also true for the light. All right. So to absorb interference in light waves, the following two conditions must be met. Okay. So the source should be monochromatic, means that it's a single wavelength for each wave. So if you try to mix them, this effect will not be as important for us, like let's say in terms of seeing the interference. So we assume here, because let's say if it's not monochromatic, see here's one wave, let's say here's another wave. So it's difficult to put them together, right? Their wavelengths are not the same, so that you can never put them together such that crest and crest, trough and trough, even if they are, let's say, in phase, starting from the same source. That's why it's important to kind of assume that it's monochromatic. They must be coherent. They must maintain a constant phase with respect to each other. That means if they are in phase, they're always going to be in phase. If they're out of phase, they're always going to be out of phase. And what do we mean by in phase or out of phase? That means, let's say if this is the first wave, and if I put the next, second one right next to that. So let's say what I have here is in phase. See, here's the second one, where if I continue, see, it kind of matches, even though it has this extra, kind of like extra wavelength of a distance. Okay, so this will be in phase. But out of phase will be if I take something and put it like this and see, their difference here is half a wavelength. That's why when they overlap, the crest and the troughs basically are together, or, trough and a crest together, and things like that. That means in phase, there are either one wavelength or two wavelengths or no wavelength. That means they're completely on top of each other. So that's, in terms of that. Now, the coherent means that once they're in phase or out of phase, they're always gonna, maintain that. So let's look at an experiment that demonstrated that light is a wave. And this is basically after, Isaac Newton did experiments in light and proposed particle model of light. Isaac Newton basically proposed that light is a particle. And since it's Isaac Newton, right, pretty much for a century or so, everybody was following that, okay, so light is a particle, even though during the time of Isaac Newton, there were some who were suggesting that light actually has some wave properties. But then in 1801, Thomas Young did an experiment using what we call double slit. So it's called a double slit experiment, where without doubt, he demonstrated that light is a wave. Okay, that means the experiment gives you a result that can only be explained if light is a wave. And that's what we're going to look at, and that's what we're going to kind of digest. So light from a monochromatic source is used to illuminate a barrier. So let's say we have this light moving towards some kind of barrier. So the barrier contains two narrow slits. The slits are small openings, and the light emerging from the two slits is coherent with, since a single source produces the light, that entering those, through those openings. Okay, so but what we have here is, if we make those openings very small, then the light will spread out from those slits when they come out to the other side. Okay, so we call it diffract. So diffraction is basically that effect when the light is spreading out from, on the other side of the opening. Okay, so this divergence of light from its initial line of travel is called diffraction. Okay, so, and one of the things you can observe on the screen when the Thomas Young did this experiment is completely contradiction of what Isaac Newton was predicting. So Isaac Newton was predicting if there's a two slit opening, right, and there's a screen, then if you basically send light, as the light enters, what you're going to see here is one bright spot over here, another bright spot over there, which is consistent with the particle model, like a bullet. When the bullet enters, right, it's going to just strike the screen in two spots. But that's not what we observe when we do this experiment. And the reason here, because the double slit experiment takes those openings to be very small compared to what Isaac Newton's experiment had. And the result here is the diffraction effect is much more visible. And on the screen, instead of just those two, bright spots, we basically observe something like this. So there are multiple bright spots. How can that be if there are only two openings? Well, it can only be if the light basically spreads out after it goes through those opening, right? So that means what we have here is this, basically. See, the light, instead of kind of going a straight line, it spreads out like this. Okay, so let's say this is, from slit one, it kind of goes like this. And then same thing happens to the source two. So let's say it spreads out like this. Okay. It's hard to do with this one. Anyways, so like that. And when they interfere, you can see now you have two waves that are interfering. So basically, that's, more complete picture right here. So when they interfere, they either interfere constructively or destructively. So this represents constructive interference. This is another constructive interference. Here's another constructive interference. And between them is the destructive interference. Okay, that means waves overlap out of phase. All right. And you can see, right, this is consistent with, interference of light, where the light as a wave can interfere, with another wave, and then they can constructively or destructively, generate a new amplitude waves. So that's kind of what we have. So you have two slits, right? So you have slit one, slit two, and those slits basically have a distance d. We're going to see, like, all that. So that there's a distance d between them. And as the light enters through them, you can see that what you have here is those red, red dots, right? So those red lines represent constructive interference. See, crest and crest, crest and crest. And where there is a constructive interference, there's a maximum, and you get that. Where the waves interfere destructively, you get a dark fringe. So bright, dark, and so on and so forth. Okay, so the light from two slits from a visible pattern on a screen, and the pattern consists of a series of bright and dark parallel bands we call fringes. Okay, again, constructive interference when the bright fringe occurs, destructive when the dark fringe occurs. All right, so before doing this, let me kind of demonstrate that there's a nice simulation that I will post so you guys be able to see. So here's what I have. See, like, let's say this experiment I can do in terms of double slit or two slits. So let's say this is a double slit. Let's make the opening small. So imagine now there's a light. So let's make it light. And let's say two slits. And I don't know, let's use red color here. And I'm going to put a screen and intensity graph as well. See, when the light goes through the opening, see, then it diffracts, see, then they overlap, and then when they hit the screen, see, then you get the patterns, like there's a bright spot, then the dark spot, right? So bright fringe, dark fringe, bright fringe, and you can see the intensity, right? Light intensity, where intensity, high when there's a bright fringe, intensity 0 when there's a dark fringe, and this basically can change, if you have, let's say, different width size, right? See, when the width size is large, right? So kind of like you have a little bit different effect. See, something like that. See, over here, you would not think light as a wave because it goes through an opening and there's a bright spot in front of that, okay? So, but when you have two slits and then it's very small openings, then what you get here, you get diffraction patterns because of the light going from those two openings, basically interfere with one another. And this is true for, different colors, you're going to say different positions for those, let's say, let's say bright spots because of different wavelength, but, you still see pretty much, similar, dark and bright fringes on the screen. All right, so I'll put this on the on canvas for you guys to play with a little bit. Now, the mathematically explaining all this, we're going to have to kind of go back and look at some of the equation we actually covered in physics 66. So let's say you have two openings, slit one, slit two. And what we do here is we have basically, this is the line that kind of goes from, okay, so this line goes from the slits to the screen. Like that, right? All right, so. Okay, so in any case, so what I have here is this. So let's say if I change, or I'm trying to change the color here. All right. Okay. So think like this. So if I take then the distance that wave one from the slit one has to travel, then this is the distance. So that's the distance. Okay. So let's call this R1. And this is the distance that second one covers, R2. It's almost hard to work with this. Anyway, so what we do here is then we do R2 minus R1, and this is the path length difference, delta R. Okay. Now, what we have here is we talked about that constructive interference occur when this delta R, which is path length difference, is equals to m times lambda. Okay. Now, for this particular case, since exactly this is at the center, right? So that means, you know, they both are exactly same distance with respect to that point of interest O, right? This one. Then R2 minus R1 will give me 0. And then the 0 is equals to m times lambda. So then how can the m times lambda be 0? It can only be if m equals 0. That means the bright fringe, the central bright fringe, has an order of m equals 0. And I know it's a constructive interference because when I divide this R2 minus R1 divided by wavelength, if I get 0, or if I get 1, or 2, or 3, or 4, and so on and so forth, I'm going to get a constructive interference. Okay, that means this will tell me if it's a constructive interference or not. Okay, so you can see, right, those two waves travel the same distance, they arrive in phase, and as a result, there's a constructive interference. And if I choose another point, if I have exactly the same thing, right? So there is a wave one who's going to travel this distance, well, and another one that's going to travel, you know, another distance, right? So let's say this is R1, and this is R2. So again, if I do R2 minus R1, it's equals to m times lambda if it's constructive. That means if I divide both by lambda, and so for this, you know, the coefficient in front of m, right? Coefficient in front of lambda. So if I get here as, again, so here I'm not going to get 0 because definitely you have different distances, right? But let's say if I get 1, 2, 3, 4, right? Then I know it's a constructive. Okay, so the lower wave travels a wavelength further and arrives in phase. That means what I have here is if I'm looking at the difference between them, so let's say if I draw this line, so this is that extra distance that wave 2 has to travel. If that's exactly a wavelength difference between them, then it's a constructive interference. That means I can say that they are in phase. So that means I have another bright fringe, and so on and so forth. That means if I continue look at some other point here, right? And I have to look at in terms of the wave 2 traveling from here to there. And then what I will find here, that distance between them, right, is now 2 wavelengths difference, and 3 wavelengths for the third one, and so on and so forth. So that means all of those waves, right, basically always going to be in phase. Now, if I look at somewhere else, and I have wave 1 and wave 2, So I do R1 minus R2, R2 minus R1. And if I divide this by the wavelength, so if I get, let's say, 0.5 or 1.5 or 2.5, then this means that those waves are, half a wavelength apart, or 1.5 wavelength apart, or 2.5 wavelength apart. And if that's the case, then what we get here is the waves when they get to point R, one will have a crest, the other one will have a trough. And that means there will be diffractive interference between them, and the dark fringe will occur. All right. So one thing then we do here is to use this mathematics, right? So then R2 minus R1 equals m times lambda. Okay, that was for the constructive. So let's say what I want to do here is, see, this is R2, this is R1. So if I draw this line over here, right? So this line over here then represents this guy here as that extra distance that it has to travel. That means we call this little like this delta, which is path length, which is R2 minus R1. But then you can see, right, there's this triangle over there where from one slit 1 to another slit, there's this distance D between them. So if I kind of blow it out over here like this, you can see that, or what we get here is the D becomes the hypotenuse of this triangle, where then I have also here the theta, which is also the same theta here, which is the angular position of that point P relative to the central line. Then what I can do here, I can say then R2 minus R1, which is delta, is also equals to D sine theta. Because theta, so this delta here is the opposite of this triangle. D is the hypotenuse. And then if you remember, right, sine of theta is opposite. So delta over hypotenuse, so D, right? That means delta equals then D sine theta. Okay. So this path length difference, delta, right? Only, we can look at when the L, and L is the distance between the slits and the screen, right? The distance here is much greater than D. Then we can basically use this, geometry, right? This trigonometry to find the path length difference, not in terms of R1 and R2, but in terms of D and sine of theta. Again, sine of theta is the angle of that point P, or makes with respect to, which is angular displacement, right? With respect to that reference line. All right, so delta equals R2 minus R1, and it's equals to D times sine theta. Okay, that means what I have here is, if it's a constructive interference, and I had in terms of R2 minus R1 equals m times lambda, but now this R2 minus R1, we say it's equals to delta, and delta also equals to D sine theta. And we do this as theta bright because this is for the bright fringe. And because it's a bright fringe, it equals to m times lambda, where m equals 0, 1, 2, 3, and so on and so forth. Now, there's also plus minus 1, plus minus 2. Now, what does that mean? Well, that means if I have a screen, behind some kind of, double slit, experiment, and this is L, right? Distance between slits and the screen. So what I will get here is when the light goes through those openings, it's going to give me a bright fringes. So there's going to be one bright fringe right here at the center. So we call this m equals 0. Then there's going to be dark fringe. But then there's going to be another bright fringe and another bright fringe. And then this is m equals 1 above, m equals 2 above. But then there's also going to be same distance as m equals 1 and others that, below the central one. And this is known as m equals minus 1. And then there's this guy here, m equals minus 2. And you can see, right, the pattern kind of goes like that. That means what you get here is plus minus to represent, is it above the central one or the below the central one? Okay. Because, for example, if I do this, right, then I get theta there. So, well, this theta is going counterclockwise. But then, for example, this theta going clockwise, so in a way, that matches, right? Because at the end, let's say if you're calculating theta, you should get negative because, let's say it is clockwise. The only way you get negative if you take m to be, plug in as a negative. All right, so this is then, again, equation for the constructive interference for the double slit, experiment. Okay, so m is called order number, and m equals 0 it is the 0th order maximum, and m equals plus minus 1 is called the first order maximum. That means there's a first one above, then first one below, then second one above, second one below, and so on and so forth. Okay. Now, for then the destructive is kind of similar idea. Remember what I have here is delta R, which is R2 minus R1. If you remember, this was for the destructive interference was m plus 1/2 times lambda. Okay. Now, since the delta R is equals to delta, and delta is equals to d sine of theta, that means then d sine of theta is equals to m plus 1/2 times lambda. All right, so that's the path difference of an odd half wavelength, and we get that. Okay, again, m equals 0 plus minus 1 plus minus 2. That's why you can see, right, if you do d sine of theta divided by a wavelength, so then what you get here is, so let's say when m is 0, so you get 1/2, which is 0.5. When m equals 1, you get 3/2, which is 1.5. And then you get 5/2, right, which is 2.5, and so on and so forth. So that's why. And what that means, whatever you get from d sine theta over wavelength ratio, right, this ratio is m plus 1/2 on the other side. So that's what you're getting. That means m plus 1/2 is equals to 1/2 only when m equals 0, 3/2 when m equals 1, and so on and so forth. All right. So these equations provide the angular position of the fringe. That means we are looking at, so let's say here's those slits, here's the screen, some distance L above, and let's say here's we get right fringe, but let's say I also get a dark fringe, right? So let's say, all right, here there's a dark fringe. Okay. So what I want to know here is with respect to that, so like the central line, what is the angular position of that dark fringe? Okay. And then this equation will give me that. So that means I can measure how many degrees it is in terms of that particular, central line. That means, let's say if it's the first one or second one, right, then I can plug in and calculate that. All right, so one thing I want to mention about this dark fringes is that, so let me draw the central bright. And then this guy here, maybe that one over there. So you can see, right, those are the bright fringes. And then I have the dark fringes basically between them, right? So remember, so this was for the bright fringe, right? So this was m equals 0, then this was m equals 1, m equals 2, and this was m equals minus 1, right? And then this one m equals minus 2. Now for the dark, so if I'm looking at the dark fringes, right? So for example, see there's one above, one below the central bright, but there is no central, dark. That means this is m equals 0 above and m equals 0 for dark below the central bright. That means first dark fringe has the order of m equals 0. Second dark fringe has the order of m equals 1. Third dark fringe has the order of m equals 2. Same thing is here. M equals 2, but negative 1. So then this will be m equals negative 2. That means what we have here is the dark fringes. The first dark fringe has m equals 0, but there are two of those, right? One above, one below. That means, oh, sorry, I missed this one here. This is m equals 1. This one is m equals 2, and this is m equals 3. Because, so you can see, right? So 1, 2, 3, 4th. That means this is the fourth dark fringe above the central one. So which m we use for the fourth dark fringe? Well, we use m equals 3. Because fourth dark fringe has, first one 0, second one 1, third one 2, fourth one 3. Okay, so try to remember that. All right. So we also can calculate something else. So let's say you can say, right, here's a point P, That means I have some kind of, pattern over there. And what I just told you, right? So you can use this d sine of theta to get m lambda, let's say, and find this theta, right, for this particular point. And this is that, angular displacement. But I can also measure its vertical displacement on the screen relative to this origin. You can think of like that, right? The central line is sort of like the origin. So this is basically becomes your zero, vertical position zero. So again, this is L, and if this is Y, and this is theta, so you have again a right triangle, and the right triangle so basically allows you to have, tangent of theta equals Y over L. That means what you have here is tangent of theta is related to the vertical position of that point P, right, on that screen. And this is measured, let's say, so this is in degrees and this is in meters. So you're kind of relating the angular position to the linear position. All right, so that means for the same position P, you can either use this equation for the, let's say, angular displacement, or this equation, if I rearrange, I have then y of m is equals to L times tangent of theta. That means I can also find its, linear vertical position. Because, sometimes you want to know the angular position, sometimes you want to know the, linear position. All right. So linear positions, right, you can see, right, are y bright equals L tangent of theta bright, y dark equals L tangent of theta dark. That means you have not two equations, because, for example, again, right, so I have then sine of theta is equals to m times lambda over d. So I can kind of rearrange this equation. So this is for the angular position for the constructive. So let's say B for bright. And this is sine of theta dark equals m plus 1/2 times lambda over d. Okay. That means those are the angular positions, and these are the linear positions for those fringes. All right. So, but one thing we have here is generally that thetas are very small. And we learned before that there's a small angle approximation that tells us sine of theta is approximately theta if theta is less than 5 degrees. And same thing is tangent of theta, approximately theta for the same reason. That means technically sine of theta is approximately theta, approximately tangent of theta. And this works if the theta is, let's say, 5 degrees or less. All right. So tangent of theta, approximately sine of theta. That means in this equation, right, that we have, I can then just replace, you can see, right, so it was y bright equals L times tangent of theta. I can say this is L times sine of theta. And what was L times sine of theta? Well, it was L times m lambda over d for constructive, right? Because it's the bright one. That means we have equation that, calculates the linear position in terms of the length, order number, wavelength, and the d. That means kind of combining those two equations. All right. So you can see, right? So we apply and we get this equation over here. Same way we can apply that for the dark fringes, and we get this equation. Okay. That means we're replacing sine of theta with the tangent of theta with the sine of theta, and then the sine of theta with whatever equation we had before. Okay. So now that means we get, this is specifically for small angles, and generally double slit experiment does give us small angles. That means we can always use this equation. All right, so let's solve a couple of examples then. All right, so Young's double slit experiment is performed with 589 nanometer light and a distance of 2 meters between the slits and the screen. The 10th interference minimum is absorbed 7.26 millimeter from the central maximum. Determine the spacing of the slits. All right. That means what we have here is we have an experiment, like let's say double slit experiment, where this is the L, and let's say I have then the central one, and then let's say, you know, let's do the bottom, doesn't matter. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And what I have here is this. This says we want, in terms of 10th interference minimum. That means we are looking for the 10th dark fringe. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. That means we're looking for this guy. And what we have here, it says, let's say this L, right? This L as being 2 meters. So when this light enters, right, the 10th, that means this guy over here is observed to be having a vertical position, right, of 7.26 millimeter from the central maximum. Okay. Again, doesn't matter if you do above or below. It's just pretty much same thing for us. All right, so we got that. All right, so that means what I have here is, remember the equation y dark is equals to, then it was m plus 1/2 times lambda times L over D, right? So we have this equation. Or we have then this, you know, a sine of theta here is equals to m plus 1/2 times lambda over D. Now, there are several ways you can do this experiment, do this example. So one of the ways you can do, let's say, right, is in terms of this, right? So to basically do in terms of like sine of theta, or that means in terms of angular, or in terms of the linear. Now the question here is this: which order m should we use for this 10th minimum, right? So 10th dark fringe. Remember, what we do here is the first one starts with m equals 0. That means this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. That means for us, this is basically, you know, in terms of 9th order. Okay. Now it says determine the spacing of the slits. That means what do we want? We want this guy, right? We want this D over here. Well, what I have here is then this equation relates all of the quantities that I have to the, you know, distance D, right? Which is the spacing of the slits. That means what I can do here is take this equation, because I am given position of the 10th minimum and the wavelength, right? That order m here is 9. That means everything then can be plugged into this equation, right? And then solve for D, because you can see, right, D is equals to m plus 1/2 times lambda times L and divided by y of the 9th order, right? And that means then from here, I can then just plug in and calculate this D. So it's then 9 plus 1/2, then times 589 times 10 to the negative 9 meters. Then this is divided by the 7.26 times 10 to the negative 3 meters, because I have to have everything in the same unit, right? Meters, and things like that. And if we do that, then we should be able to calculate this to be 1.54 times 10 to the negative 3 meters. All right. So that's the answer for this problem. Okay. And I think I had basically have some pictures over there, but anyway, I drew those pictures. So that means what we did here is we found all the given information, we found the equation that we want, and find the D. On the slides, I have different method of using this. So they specifically use this different, like alternative method of finding D, so that you have the two ways of, calculating the same, same thing. So, all right, so here this was basically the diagram that kind of have. All right, so let's look at another one. So you have a pair of narrow parallel slits separated by 2.25 millimeter, are illuminated by a green light at a wavelength of 546.1 nanometer. Then the interference pattern is absorbed on a screen 1.2 meter away from the plane of the parallel slits. Calculate the distance from the central maximum to the first bright region on either side of the central maximum and between the first and second dark bands in the interference pattern. All right. So basically, here's our experiment again, right? So we have a source, there's a double slit, and this time we're given the distance of the slits, right? The spacing, 0.25 meters. And we given L between the length, between the slits and the screen to be 1.2 meters. And we basically observe something, those dark and bright fringes. So what we're given here is D equals 0.25 meters. We're given wavelength equals 546.1 meters. L is equals to 1.2 meters. And what we want to find for part A is the distance from a central maximum to the first dark region. Sorry, first bright region, okay? That means, let's say this is being the central one, m equals 0. Then what I want here is for m equals 1 or m equals 1 minus 1, right? This is for a bright. That means I will have m equals 1 on either side. That means if I want to find the distance, right? The distance from one to another, right? Distance from the central maximum to the first bright fringe. And that means that then the distance from the central maximum to the other bright fringe, at the bottom, right, is exactly the same. So let's do that. Then what I can do here is use this equation, y bright is equals to m lambda L over D. All right, so again, taking that m equals 1, so becomes 1 times 546.1 times 10 to the negative 9 meters. Well, here is nanometer. Then times the 1.2 meter length. And this is divided by the spacing of 0.250 meters. Okay. Well, if I calculate this, I'm going to get 2.62 times 10 to the negative 3 meters, which means the position of the first bright fringe. So first bright fringe is equals to 2.62 millimeters. All right. Now the question B, part B says what is the distance between the first and second dark bands in the interference pattern. Now here you have to kind of understand this. So basically, if this is the central one, and then let me maybe use a different color. All right, so if this is the central one and this is the first bright fringe, then distance between them, right, is exactly that. Distance between them is exactly that. Now, if I go to the other side for the next bright fringe and the other side, this distance between them is also exactly that. Okay. Now, how about from the central one to the first dark fringe, so like in the middle? Well, it's going to be y dark one is going to be then half of y bright one, right? You can see, right? It's exactly half the distance. So you kind of can see that. Then what I have here is So this is the first dark fringe, right? So this is the first dark fringe. That means the distance of the first dark fringe from the screen is half of the, half of this, which is basically, what is it, roughly 1.31 millimeters, right? Then what I have here is then, this is then the second bright fringe. Oh, sorry, second dark fringe. Well, second dark fringe is then going to be, you can see right from the central one, right? Or you can see right between first dark and the second dark. So it's basically going to be this distance. So we want basically pretty much that distance. What is that distance? But you can see that what I have is just like from one bright to another bright. This is the distance from one bright to another bright. Then from one dark to another dark, I'm going to have exactly same distance. Because see, like I know that from dark to bright is 1.31. That means if I go from here to there, I'm going to get 1.31. And then from there to here, another 1.31. That means this total distance is 2.62. That means what I have here is then delta y for any bright or delta y for any dark is exactly going to be the same. And in this case, it's going to be 2.62 because this 2.62 was the measurement from central to the first, let's say bright, from 0 to 1. So this was 2.62. That means if I look at the third bright, what is the distance of this third and the, second bright and the first bright? This is also 2.62. About the third one, this distance also 2.62. That means the spacing between them will exactly be the same as the spacing between m equals 0 to m equals 1 for the bright, or m equals 0 to m equals 2 for the bright, m equals 1 for the dark. That means they're all going to be having the same spacing. And that's kind of what we have in this example. All right, so the last kind of thing that we want to cover in this chapter is a diffraction pattern using the single slit. Okay, so this is when it's going through the small opening, just one opening, right? And what we have here is the diffraction refers to the general behavior of a wave spreading out as they pass through a slit. Okay, and diffraction pattern is really the result of this interference. Okay, so what I have here is a single slit placed between a distant light source and the screen produces a diffraction pattern. Okay, now it doesn't have the same pattern as the double slit. So that for the single slit, there's a very broad, intense central maximum. That means bright central maximum dominates all the other bright ones. The other bright ones are barely visible. And the central band will be flanked by a series of narrower, less intense secondary bands called side maxima. Okay, so what we do here for the single slit, we are more interested on the minima, which is dark one. So the central band will also be flanked by a series of dark bands called minima. Basically something like that. So we have Fraunhofer diffraction pattern occurs when the rays leave the diffraction object in a parallel direction and the screen very far from the slit. Could be accomplished by converging lenses, and the dark bright fringe is seen along the axis at theta equals 0, that central bright one. And alternating bright and dark fringes are set on each side. So general condition for distractive interference is given with this equation. That means for the single slit, we do not care about bright, maximas. All we care about here is the distractive interference. That means we want to know, where is this guy? Where is that guy? Where is this guy? Where is that guy? That means only for the dark. And the equation for the dark ends up being A sine of theta equals m times lambda. For the dark is actually happened to be this for the single slit. So this is for the single slit. And if I divide both sides by A, basically, then I'm getting sine of theta dark, as you can see over here. There's also no m equals 0 for the single slit. That means this is 1, this is 1, negative 1, this is 2, this is negative 2, and so on and so forth. Okay. So let me maybe show this simulation again. You guys can see. We go back to this. So if you restart, but this time we have a single slit, as you can see, right? So you can see right as the light goes, what we get on the screen, let's do light, because then we can do screen and intensity. All right, so let's go. As you can see, right, it diffracts again. When it hits the screen, you can see right on the screen, then you get really broad central maxima. Okay. So if I make this a little bit smaller, even if it's different color, right? Maybe not that good. So something like this, you should be able to see that. So as it diffracts, see there's a very, broad central one. And you can see then the, in terms of the pattern and intensity on the screen. All right. And you can see right there, if I can, you can open and close the, or make it bigger, or, smaller, the width size. And you can see right now as if the opening is, opening is large, right? So you get, large intensity at the center, right? So, but as you make it smaller, you still get, diffraction, right? You can see kind of like holding like that. All right. So go back. So that's kind of what we have. That means for the single slit, we are basically looking at that. So we are looking at the dark fringes, okay? And the dark fringe is basically going to be in terms of, so you can see right there's a very broad central right fringe, but what we're looking for are those guys, those positions for Y1, Y2, right? That means we're looking at the dark fringes, okay? So just like that double slit experiment, we could find the position in terms of, theta and, vertical position. Here we can also basically do that second equation, right? Y for dark is equals to m lambda over a. Okay, so we can also, use, L. We can also use this equation, right, to find the vertical position. That means you have, like, let's say the sine of theta is equals to m lambda over a. And generally what we do here is, remember, so technically one thing I can say here is that theta is small, so I can, in a way, find the angular position both for constructive and destructive, right? And sorry, for the double slit and single slit, in terms of theta in radians rather than sine of theta in degrees, because angles are very small. All right. That means this equation for the theta is the position with respect to the angular position, right? The second one is a linear position with respect to that zero. That means that the reference line, zero, right, can be used to get, position in terms of angular and linear. All right, so let's look at a few examples here. All right, so you have a coherent microwave or wavelength 5 centimeter enter a tall, narrow window in a building, otherwise essentially opaque to the microwaves. If the window is 36 centimeter wide, what is the distance from the central maximum to the first order minimum along the wall? 6.5 meter from the window. All right, so let's see what we get. So we are told that the wavelength is 5 centimeters. Okay, well, that's because it's a microwave, not not a visible light. We are given that the window is 36 centimeter wide. Okay, that means that's basically our opening, A. Okay, and we're told that from this, what is the distance from the central maximum to the first order minimum along a wall? 6.5 meter from the window. Okay, so let's say here's a window and here's a wall, right? That means this distance L is 6.5 meters. All right, so we have this, couple of ways to do this, right? Again, you can use this sine of theta equals, m lambda over, a, and then y equals L tangent of theta. So I think in my slides, I have different ways where I can use this to find the theta. And generally probably here is a good idea because the theta might not be too small. Remember, so whenever you're doing theta, there is a few degrees, then sine of theta equals theta. But when theta is 7, 8, 10, 20, 30, right? Then maybe it's better to just use the sine of angle rather than the angle itself. So for example, in this equation, I take the sine of theta and say it equals to m lambda over a. And I have all of those values, so I can then solve for theta, which is inverse sine of m lambda over a. Okay, so inverse sine, plug in the values. Well, the first order, right, remember in this case is just 1, then times the wavelength, 36 centimeters. I can keep it centimeters because the other one is also centimeters, and then wavelength is 5 centimeters. Okay. Oh, sorry, other way around. So this is 5 centimeters, and this is 36 centimeters. Okay. So we find the theta to be 7.98 degrees, or let's say 8 degrees. Okay. So it's greater than 5 degrees. That means we rather use the theta, sine of theta and tangent of theta. Then y is equals to L tangent of theta. So L is 6.5 meters. Then tangent of, let's say 8 degrees, right? And what we get here is roughly 0.91 meters, or 91 centimeters, let's say. Right? That means 91 centimeters from the central, you will see then the first dark fringe, which is like a meter away, pretty much, almost. All right, so one more example here. A screen is placed 50 centimeters from the single slit, which illuminated with light of wavelength 690 nanometers. If the distance between the first and third minima in the diffraction pattern is 3 millimeters, what is the width of the slit? All right, so let's see what we're given. We're given the screen is placed 50 centimeters from the slit. That means L is 50 centimeters. We're given wavelength 690 nanometers. And then we're given then delta Y between first and third. That means Y3 minus Y1 is equals to 3 millimeters. Okay. That means, we need to, let's say, do this calculation and find in terms of what will be the, let's say, the delta Y. Okay. Now, one of the things we have here is, so you can pretty much do this calculation, right? So let's say Y3 here is, remember, where Y here is M lambda L over D, right? So let's say one of the things you can do here is say, okay, so Y3 is equals to 3 times lambda L over D. Y1 is equals to 1 times lambda L over D. Okay. That means delta Y in this case will be 3 lambda L over D, right? Then minus lambda L over D, because, M equals 1. What we get here is 2 lambda L over D. Right, so we get 2 lambda L over D. And that's what we want, right? So let's say in terms of the, oh, sorry. It's A, not D. So a D here is for the double slit. For the single slit, we're always using A. Okay, that means delta Y here is equals to 2 lambda L over A, and then just rearrange and solve for A, which will be then 2 lambda L over delta Y. And this will be 2 times 690 times 10 to the negative 9 meters. Then L here is 0.5 meters. Then this is divided by 3 times 10 to the negative 3 meters, which is in terms of the distance between third and the first one. All right, so we calculate A is equals to 2.3 times 10 to the negative 4 meters. And that's basically the width of the slit for that single slit example.